I have to put on my recording. Okay. And what we're seeing over here is the X-ray tube encased in the a metal housing with the oil surrounding it for heat dissipation purposes, then to which we attach a collimator. Within the collimator you have a mirror, and that mirror then reflects light onto the patient to indicate where the X-rays will enter the patient. And what we're saying is that that is so significant that there are laws stating the maximum deviation. You cannot be off by more than 2% of SID. The universal SID is 40 inches, 100 centimeters. So you can be off 2% of that, or around 0.8 of an inch, a little bit less than 1 inch, so that the tech doesn't meticulously have to adjust the X-ray beam to the actual image plate. He can be off by 0.8, about an inch. And that's what they usually give themselves a little leeway of around an inch. The other SIDs that we use for an upright chest system is typically 72 inches, and 2% of that would be 1.4 inches. The take-home number here is 2% of SID. The take-home concept is that the light field should coincide with the X-ray field. Why? For purposes of reducing patient dose. Okay, 65 centimeters is a number to remember for mammography. That's pretty much the universal SID that we use in mammography, and again, it would be 2% of that. This is just a picture of, actually it's one of the machines in your department. When I was working in your department full-time, what you see is the X-ray tube and the metal housing. Here are the cables that, for instance, this is the anode cable, and over on the far side you can just barely see the cathode cable. They give you the electrical supply to the X-ray tube. Here is the collimator. These set of louvers over here is a fan. You're actually blowing air across the tube. That turns out to be another heat dissipation mechanism. Try to keep the oil as cool as possible. Within the collimator, you have the motion controls. You got to move the X-ray tube back and forth to position it over the right position over the patient, and a scale telling you the sizes of the X-ray field, and in one direction. This is the control for that, and the indicator, scale indicator here, and the other direction over here, again with these scale indicators indicated. Okay, and I've indicated on this particular system, which I don't particularly like, you have a filter slot. We're going to be talking about filtration later on. You can add more filters if you so like. Just stick them into that little slot in this particular design. I don't particularly like that, because if you do put in a filter, for whatever reason, when you move this tube around, it's possible that that filter fall out, and then everybody thinks that they have the correct filtration, and they may not. We'll be talking about filtration presently. How about another source of radiation? The leakage radiation. Leakage radiation, remember that you're producing X-rays at the target, and the target doesn't produce X-rays just directed toward the patient, given by this the red arrows over here. X-rays are produced isotropically. They're produced equally, ISO, in all directions. And so what that means is that you could have leakage radiation hitting the patients in positions, just delivering a dose to regions of the patient that are not involved in the examination. And they represent a hazard to the personnel and a hazard to the patient. We have to control that leakage radiation. And again, that is so significant that we add lead. We add lead to the tube housing. That's how we control that leakage radiation. So that these green arrows, which represent the leakage radiation, has a means by which they can be shielded against. And all the law books say that you have to have a maximum of 100 mR per hour at 1 meter average in all directions, that, as a maximum to your leakage radiation. I think that's a pretty generous amount. I've never read more than, maybe 2 to 3 mR per hour in any one direction. But that's your limit, 100 mR per hour at 1 meter. And the way we assure that is by that lead inside of the housing. This is what it looks like. And you see the lead here in orange, and lining the X-ray tube. This goes completely around the X-ray tube, so that there's your protection for your leakage. On this particular design, notice they don't have lead in the back over here. Presumably the X-rays are produced mainly in this direction. The X-rays would have to go through this target, which is a high atomic number tungsten target, to be towed the back, so that would be a filter shield incorporated right into the target itself. Notice that you see the indicator of oil. There's an oil bath completely around this X-ray tube. Okay, let's continue looking at X-ray beams. We've mentioned leakage. We've mentioned the primary beam. We've mentioned the non-coincident beam, the X-rays that don't coincide with the light beam. But now let's look at scatter. When radiation hits the patient, it scatters. It goes in every which direction. And so what? Well, some of that scatter, given by these arrows A and B, arrive at the image plate, and they serve to degrade image quality. Some of the scatter goes beyond the patient in other directions, and for instance, can expose you off in the room. For instance, if this was fluoroscopy and you're nearby, you're going to be exposed to a scatter. Scatter degrades image quality. We hate scatter. It's the biggest source of image quality loss in radiology. We go out of our way to minimize and to potentially eliminate scatter from our images. It provides that personal hazard that we were just mentioning. That's why you wear your lead aprons and your thyroid shields. That's why you put lead around the walls and those panoramic windows that you find in the interventional suites. Those are acrylic materials with lead impregnated within them. You have to protect against that scatter radiation. And you have the personal hazard not only of people inside the room, but outside the room, the environment of the room. And you have to provide lead in the walls. Here you see a scatter being produced in all directions. Scatter is also pretty much isotropically produced within the patient, and that will require lead shielding around the room and around the control area to protect the tech. And we also have to worry about the primary beam. Here you have, in an upright chest stand, the X-ray source is directed toward this wall. Who's standing on the other side of the wall? They're going to be exposed by the primary. Again, you're going to need lead in the walls to protect for both the primary and the scatter radiation. Here's another radiation beam that you should be familiar with. Here comes an electron coming in from the filament, hits the target, produces the primary X-ray beam. That's good. But a certain fraction of those electrons, when they hit the target, bounce off of the target, and then they get re-accelerated back to the target, but they'll hit points not at the focus. And we call that off-focus radiation. When the electrons hit this point that's not at the focus, it produces an X-ray beam there as well. High-energy electrons hitting a target will produce X-rays wherever they happen to hit a target. Here we see it in green. Well, so what? Well, those off-focus radiations serve to expose the patient. So how do we get rid of that? First of all, notice I've showed here two things. Number one, there is an aperture that we can include in the column, and I'll show you a picture of that in the next few slides. and to knock off some of that off-focus radiation. But notice, and this is the important one point for us in imaging, notice that some of that off-focus radiation falls within the field, That means it arrives at the X-ray image and serves to degrade image quality. It doesn't coincide with the true primary beam given here by the red. This green is that off-focus radiation. So if you have a tube that produces a lot of off-focus radiation, you're going to have a problem with image quality. We try to minimize the problem with these primary apertures to minimize that. But you can still have, as we just mentioned, some of that off-focus radiation falling within the actual image field. Okay? Here you see this particular radiation ray that was not eliminated by this aperture, going beyond the X-ray field. Why, that'll just give a dose to the patient totally unnecessarily. Doesn't add to the image information. Okay, so again, off-focus radiation is a bad radiation. Okay, where is this primary aperture I just was mentioning? It's right up into the oil. The collimator has a set of shutters that sort of conically shaped like this, and they stick right up into the oil as close to the X-ray tube as possible. You can't touch the X-ray tube, but almost touching the X-ray tube. The closer that aperture gets, the more cleaner it will, the more effectively it will remove and clean up that off-focus radiation. Okay, this is what it actually looks like. Here's a collimator, this protrusion you see here in the darker colors is a series of lead little bars. They're sort of set up like in a little pyramid, a little conical section. As you control the shutter size, the actual lead shutters are down here someplace. As you control the shutter size, those shutters are mechanically linked to the primary aperture. So as they open and close, so does this primary aperture. And notice it goes beyond the surface of the collimator right up into the oil. This is what an image looks like if you have off-focus radiation. Notice that you've collimated down to a primary field, but where did this anatomy come from? Where did the radiation that went through the patient tissues and delivered information to this plate, but yet was not desirable? It was not the desired information. The desired information falls within the primary field. You see, you can check your systems for this off-focus radiation by going to a collimated field. If your field covers the whole X-ray image field, well, then you won't be able to see the information outside of it. So most of the time, you do have the image covering the whole image plate and the whole image field, so you really don't know how much off-focus radiation the patient got exposed to. You really don't know how much off-focus radiation is falling within the image field and degrading the image. Okay, you only see that with collimated fields. Maybe you've seen these collimated premature infants fields where they want a chest film and they collimate down to the chest film, and the image plates are larger than the collimated field. So again, now under those conditions, you can see some off-focus radiation. Look at the other side of this field. Pretty clean. Very little, if any, off-focus radiation on that side. Over on the top and on the bottom, we can't tell because the X-ray field goes right up to the edge and we're not quite sure what goes beyond the edge. Okay, so here's a summary of all the beams that we talked about. The primary beam is the only good beam. It contains all the patient information. That's your image. And then you got the leakage radiation. You've got the non-coincident radiation, non-coincidence in the X-ray field and the light field. And then, as we just finished discussing, the off-focus radiation. Let's get now onto X-ray production. How do you actually get the X-rays? We've been looking at the big picture. The big picture is get electrons from the filament, fermionic emission, accelerate them across the tube, have them impact the target, and convert the kinetic energy of those electrons to X-ray energy. Later on, we're going to talk about what do we do with the heat energy. We already saw that the bulk of that energy goes into heat. But let's concentrate now on how do we actually get the X-rays. There are two possibilities. Remember, we have electrons impacting, interacting at the target with some target material. Okay? Well, a target material, what's that? It's atoms. And what are atoms made up of? Electrons and nuclei. So as these electrons enter the target, they either interact with orbital electrons or they interact with nuclei. That's what we're going to be looking at. Here is when you have the incident electrons interacting with the nucleus, what occurs, the mechanism or interaction that occurs is called Bremsstrahlung. When you have those electrons interacting with orbital electrons, then you have characteristic radiation production. These are the only two mechanisms of X-ray production that are applicable in X-ray imaging: Bremsstrahlung and characteristic radiation. Let's look at what is actually happening in each specific case. Let's look at Bremsstrahlung first. Here comes an electron coming in from the right. Let's assume that the kinetic energy that's coming in is 100 keV. And by the way, how does an electron get 100 keV? That's 100,000 electron volts. Well, remember the definition of electron volt? I'll define it for you again. An electron volt is the energy acquired by an electron falling across 1 volt. If you have 1 volt, you get 1 electron volt. If you have 100,000 volts, you get 100,000 electron volts. It's the same number as the voltage. You just stick an E in there, and that'll tell you the energy that that electron carries. It's the volt. It's numerically equal to the voltage. So the answer to the question, where does an electron get 100,000 electron volts? By being accelerated across 100,000 volts. There it is. Well, here it comes, and it's coming near a nuclei of the target material. Now, what is going to happen when you have a negative electron coming near a positive nucleus? What did your junior high school teacher teach you about opposite charges? They attract, right? Like charges repel, and unlike charges attract. So there'll be a force of attraction exerted on this electron, and that force on that electron will cause that electron to deviate from its path. It's going, and in the process, it's going to lose energy. Just visualize yourself in a car coming up to a right-hand turn. What do when you come up to a right-hand turn? You start slowing down to handle and maneuver that curve. This electron goes slowing down. It starts putting on the brakes, just like you do to handle a right-hand turn. Look at the word Bremsstrahlung. The word Brems in German is braking. Strahlung is radiation. Braking, radiation is the literal translation of this term. Bremsstrahlung, braking radiation. It's the sudden slowing down of electrons. If they slow down, they lose energy. And where does that energy appear as? You just produce X-rays. And here is a sample situation. If you came in with 100 keV and you get slowed down to 50 keV, where did the other 50 go? Into an X-ray photon whose energy is equal to that amount of energy. You started out with 100. Notice you still end up with 100. Oops. Okay. I'm going in the wrong direction here. Okay. Okay, back to this. Okay, well, what if that electron was going a little closer to the nucleus? Well, if it's going a little closer, like I've shown here, in a pathway 2, if it's getting a little closer, there'll be a greater force of attraction exerted on the electron. Greater force of attraction, there'll be a greater deviation of its path. There'll be a greater amount of slowing down, loss of energy. The more energy that electron loses, the more energy the X-ray photon acquires. Look at the split over here. You start out with 100. The residual electron has 20 keV residual energy. X-ray photon, 80 keV. So now we've produced another photon, but this time of a higher energy. How about the one I showed in pathway 3, where the electron is so far away, there are no forces exerted, there's no deviation of the trajectory, and therefore there's no loss of energy, and there's no production of X-ray energy. The X-ray energy is zero. It doesn't exist. Okay, I'm going to put in the other extreme. How about an electron that's in a collision course? Go right in collision course with the nucleus. What happens now? What will happen is that the electron will bounce off the nucleus, will be reflected right back to its source. Here, it's like a 180 degrees a reversal of direction, and it represents the highest energy loss. You can't lose more than the energy that you started out with. You can't be deviated by more than 180 degrees over here, so that the kinetic energy of that electron is approximately zero. It's not exactly zero, because after all, it's still moving, so it must have some kinetic energy, but relatively little. And the X-ray photon goes off with its maximum energy, approximately equal to the energy that the electron came in with. Can't be exact, because the electron has some residual energy because it's moving. Okay, there's your Bremsstrahlung. The point to be indicated here is that this electron can approach this nucleus at any arbitrary distance, can be deviated by any arbitrary angle, can lose energy by any arbitrary amount with a cap at 100, right? It goes between 0 and 100. And at every point, the conservation of energy applies. Here down at the bottom in green is a statement of that conservation of energy, where the X-ray energy plus the kinetic energy out is equal to whatever came in. Okay, and in general, that X-ray energy photon, as we mentioned, goes up as that angle of deviation goes up. Okay, let's give an example. Let's say that you had a voltage of 100 kVp. First of all, what's the kinetic energy of the electron if it is accelerated across a voltage of 100,000 volts? And by the way, we specify our voltages in terms of the peak values. They actually are changing. We're going to be talking about that presently, but we talk about the peak value. Well, what's the kinetic energy then? Well, then if you set 100,000 volts, you get 100,000 electron volts. We mentioned that. What's the maximum energy that the kinetic and that the photon can have? The maximum energy a photon can have is the maximum energy the electron delivers to the target. In this example, 100. Okay. If your X-ray, what's the energy of the X-ray if the kinetic energy out is 60? Well, remember that you got to add those two up, and the sum has to be 100. So if you started out with 100 and you can account for 60, where did the other amount go? That went into the X-ray photon, 40 keV. Okay, let's move on. Because that electron can approach the nucleus at any arbitrary distance, that means there can be any arbitrary angle of deviation. So if we plot the number of X-ray photons produced as a function of their energy, typically you get what we call this polychromatic distribution. Poly meaning many energies, many colors, many energies. All energies are present up from 0 up to the maximum energy. And we just saw that the maximum energy was numerically equal to the voltage. Okay. So a very important observation. Bremsstrahlung spectra are polychromatic. They are continuous. They have all the energies present from 0 to the maximum, but, here's a big but, they have all the energies present, but not all energies are equally present. Okay? There's very few very high energy photons, and there's very few low energy photons. They're concentrated in this region over here, not quite in the middle. They're concentrated about 1/3 of Emax. The average energy, the mean energy, the effective energy runs about 1/3 of the Emax. It coincides pretty much with the maximum number of photons. You know, at what energy do you have a maximum number of photons? And this relationship, 1/3 of Emax, applies only at the surface, the incident X-ray energy distribution. Okay? We're going to be talking about what kind of energy distribution exists inside the patient, but on the surface of the patient, about 1/3 of Emax. Okay? Okay? Well, that's your Bremsstrahlung, and it yields polychromatic spectra. Let's now look at characteristic radiation. Remember, those are the interactions with orbital electrons as compared to Bremsstrahlung, which was interactions with the nuclei of the target material. But these, notice the big difference here, the characteristic radiation is going to yield monochromatic spectra. Let's take a look at that. Here comes an electron coming in from the right, certain amount of kinetic energy, just like before. But now what if it hits an orbital electron, interacts with an orbital electron? Well, here you see then that if that incident energy, it has enough energy to overcome the binding energy, then it'll knock the electron out. And then you'll have two electrons in motion, right? The one you just knocked out and the one that was coming in. And the energy balance for that interaction would be just that simple sum. Kinetic energy coming in is going to be first, invested in removing that orbital electron. That means it'll take a certain amount of energy, the binding energy of that particular orbital electron, and then whatever's left over goes into the kinetic energy, which in this case is split between two electrons. Okay, here's an example. Again, we have 100 kVp, and we know we're given that the binding energy is 69. By the way, that is the binding energy of tungsten. In the next few slides, we're going to be talking exclusively about tungsten. Later on, we're going to expand our thinking to other types of materials, but let's stick to tungsten for now. Given what those two parameters, what's the maximum kinetic energy of the electron reaching the target? This is a replay of what we've already done. It's always equal to the kinetic energy in. And what is the kinetic energy in? It's the voltage. And in this case, the peak voltage would be 100 keV. So 100 kVp, which will yield 100 keV at the E max. Okay. B, determine the kinetic energy available for the ejected electrons. Let's use our little conservation of energy form. You came in with 100. It took 69 to knock out the electron. That was the given binding energy. And then how much energy is available for the ejected electrons? 31. And if they're split evenly, that means approximately 15.5 keV each. But it's a total split between two electrons. Okay. Well, it gets even richer than that. What you see over here is let's start out with this red arrow here. You just emitted or ejected an electron from the K-shell of this tungsten target. We saw that it had a binding energy of 69, and you created a vacancy. See, we don't have X-rays yet. Where do the X-rays come in? This is where they come in. You created a vacancy. There'll be a tendency of the electrons from higher up to fall down into those vacancies. Stop right there. When an electron changes energy levels, it has to surrender the difference in energy levels. So that if the 69 keV and the binding energy of the L shell is 11 kV, and you have a transition between those two shells, the energy difference is 69 minus 11, or 58 kV. 58 kV is the X-ray photonic energy that you just produced. Mission accomplished. You have X-rays, and you have it of a specific characteristic energy. That's why we call this characteristic radiation, because only tungsten will yield an L to K transition equal to 58. Only tungsten has 69 in the K shell. Only tungsten has an 11 in the L shell. Only tungsten will have that difference of 58. But now you've created a vacancy in the L shell. Well, then an electron from higher up will fall there. And again, you have characteristic radiation. Look at the bottom statement here, equal to the difference in binding energies. In this case, since the M shell is 1 keV for tungsten, it's 11 minus 1, or 10 keV. Why? Now you've got a second X-ray photon, this time equal to the 11 minus 1, or 10 keV. But now you have a vacancy in the last shell. Well, an electron can be floating around. Typically, we refer to those as electrons at infinity. They're not really at infinity. They're just not bound. They're just floating around. Remember, you have X-rays knocking out electrons helter-skelter. So there's lots of electrons floating around that had been removed from their shells by the incident X-ray photons. So one of those free electrons, unbound electrons, can fall into that last shell. But again, you always have to have difference in binding energies to form that characteristic radiation. Now you have 1 minus 0, or 1 keV being formed. There's your third X-ray photon. And by the way, the 1 keV is so low energy, it's not even going to leave the X-ray tube. It's going to be absorbed in the glass. And if it's not absorbed in the glass, it'll be absorbed in the oil. And if it's not absorbed in the oil, it'll be absorbed in the mirror. It'll be pretty much a non-entity. It won't escape from the tube. But you did produce 3 photons along this particular pathway. But there's other pathways. And now I'm going to indicate before we go there, notice that if you add up the sum of these 3 photons, let's do it, 58, 10, 1, you see they add up to 69. Here is another a statement that's always true. Along any particular pathway, the sum of all characteristic radiations is equal to the initial binding energy. We're going to show that for all these other possibilities. It is always true. They always add up to the initial binding energy. Let's indicate the most important transition for us. The most important transition for us is the one that yields the highest characteristic radiation energy. And that one would be a transition from infinity going straight, hopping over the M, hopping over the L, going straight down to the K. So now notice that the difference in binding energies is 69, the K shell binding energy, minus 0, the unbound electron. Binding energy is 0 for an unbound electron. 69 keV. So that represents the highest energy, and also turns out to be the most important one for us. Okay, and if you add what's the total characteristic radiation there? 69. All pathways will always equal to the initial binding energy of the electron that started the process. And what we just saw, the transition from infinity to the K shell, answers 2 important questions very common on the boards. Here's one question. What transition yields the highest possible characteristic radiation in any atom? Answer, from infinity to the K shell. That's true all the time. Here's the second most important question. What is the energy of the highest characteristic radiation from any atom? Answer, the K shell binding energy, okay, as we just seen. Here's another possibility, another pathway. What if you have an L to M transition? That'll give you the 58 keV. But now an electron from infinity hops over the M, skips over the M, and falls into the L. Well, there's a different possibility. You still get the 58 from the L to K. 69 minus 11 is still 58. But now you go from 0 to 11. Now you got 11 keV. 11 keV. And again, if we add those two up, 58 and 11, again, it adds up to 69. Here's the last one I want to indicate over on the right. What if you had an electron from the M shell hop over the L and drop into the K? So now you have 69 minus 1, 68 keV. Very similar to the one from infinity to the K. And then finally, from infinity to the last shell gives you 1. But as before, 68 plus 1, again, total of 69. Those are the most important ones for us, and I've particularly indicated the one on the far left, the one that yields the highest energies. But all these pathways are happening simultaneously at all the various atoms that are being radiated by these electrons. So you produce all these X-ray photons, but let's make the spectra of those photons, and that's why, as you see from this graph, we call this monochromatic. Notice that you have discrete energies. Remember the numbers we mentioned? There was a 69 and 68. I'll just call it 69. There was a 58. There was an 11 and 10. I'll just call it 10. And then there was a 1. I'm not even putting that there. It's so low down here and not important. So this is a typical spectrum from the tungsten target, purely monochromatic. It's either a 10, a 58, or a 69, and those are the only possibilities for characteristic radiation from tungsten. We say that it's discrete energies, and the energies of those characteristic radiations depend on the atomic number. The higher the atomic number, the bigger or the larger the binding energy. The larger the binding energy, when you look at a transition from 0, the unbound state, to the K shell, the larger the characteristic radiation energy. And in general, the greater the binding energies of all the shells, the greater the differences between the binding energies of those shells. So this is always true. Characteristic radiation goes up as atomic number goes up. Okay? Well, let's put those all together. We've got the Brems, which is polychromatic. We've got the characteristic, which is monochromatic. I've indicated some other synonyms for the polychromatic. Sometimes we call it continuous spectra. Sometimes we call it heterogeneous because it's so different. And then over on the right, discrete and homogeneous. And if you put them together, this is what it looks like. Remember, the X-rays come out of the X-ray tube and are incident on the patient, and looking at the totality of the spectrum, it would look like what I've indicated over here. And notice that the prominent distribution is the underlying Bremsstrahlung distribution, the continuous distribution that goes from 0 to the peak and then down to the Emax. Notice that typically, in terms of number of photons produced, by far, Bremsstrahlung predominates. 80 to 90% of all the interactions are via Bremsstrahlung, and only 10 to 20% via characteristic radiation. So there's your final looking target from tungsten. Where do we use tungsten? In CT scanning, in radiography, in fluoroscopy. And there are other target materials, for instance, in mammography. Let's turn our attention to mammography now and other target materials. But emphasize tungsten for CT, fluoro, radiography, and now we're going to consider other target materials for mammography. Why even consider other target materials? Because in mammography, we have a very unusual problem that is not present typically in radiography, CT, or fluoroscopy. And that is that you have a relatively uniform distribution of tissues within the breast, which means that the tissues are not very much different one from the other. I now introduce an extremely important concept, the concept of contrast. I'm giving it by this letter C and giving it the sub letter S for subject contrast. Here's a definition, a working definition of subject contrast. The ability of a tissue to distinguish itself from the surrounding tissue. Can you see the tissue in its normal anatomical background? Will you be able to see that cluster of calcifications? Will you be able to see that mass? Will you be able to see the various breast structures? In mammography, you have a tremendous challenge because your ability to see tissues, to distinguish one tissue from another tissue depends on how different they are, how different in density, how different in atomic number. In the breast, they're very similar, so there's very little subject contrast. So now the question is, how can we maximize our contrast? How can we make it easier to see the anatomical structures that we desire to see? Well, later on in another chapter, I'm going to give you the proof of the following observation, the following principle, and that principle is if you lower the X-ray energy, if you image with a lower voltage, you will get more subject contrast. Mammography universally is done at much lower voltages than we do at CT, radiography, or fluoroscopy. Why that should be so? We'll see in chapter 5. Okay, but now the downside. Yeah, you can get more subject contrast by going to lower energies, but in the process, what do lower X-ray photon energies, what happens to them as they go through tissues? They get absorbed. And what is absorbed energy per unit mass? Dose. Dose goes up as energy goes down. And that's very intuitive. A low energy photon is very easily absorbed. It'll go into dose. Well, now the question is, okay, we have to go down in energy to maximize contrast, but we don't want to go too low because the dose will go through the roof. So we go through an optimization procedure, and we come up with the calculation of what would be the optimal energy for a typical breast, typical thickness, typical composition, which is considered a 50% soft tissue, 50% fatty tissues, and the optimal energy is as low as we dare go and yet still keep dose within a reasonable amount. That number is 20 kV. 20 kV is the optimal energy for a typical breast. Well, how do you get 20 kV? Well, I've already given you one way of getting 20 kV. How about this way? Remember we saw that the average or effective energy is 1/3 of the maximum? Well, if you want the average to be 20, the desirable optimal energy, well, then just set 60 volt kVp. 60 kVp will give me 60 kV at the maximum. Notice that the maximum is always numerically equal to the kVp. Well, then 1/3 of 60 is 120. Mission accomplished, right? Wrong. That is not the way we get the 20 kV. And why? Because, yeah, you got an average of 20, but notice that along with the 20, there's lots of photons that are going to be passing through the patient and giving a dose. Those low energy photons are going to be absorbed within the patient. So your quest for the 20 via this pathway will give a lot of dose to the patient because of all those low energy photons. Remember, the 20 is an average. There's lots of energies beneath the average giving a dose, and there's lots of energies above the average. And what do? Now these are photons that will get through the patient. They're higher energy photons. They'll get to the image plate, and they'll contribute to the image, but with a very low subject contrast. They'll take up space in the image, but not yield very much information. So this is not the way we want to go. Well, time is, I'm going to take a couple of minutes to finish up this thought. What would be the ideal? What would be the ideal? The ideal would be if we could only conjure up an X-ray beam that is strictly 20 keV, no less, no more. Every single photon is exactly the optimal energy. If we could only have that kind of spectrum, a purely monochromatic spectrum. Well, we don't have those kinds of beams. We always have a Bremsstrahlung. We always have energies below the optimal and above the optimal. But isn't this reminiscent of characteristic radiation? Okay, maybe we can have a target material that at least has a concentration of these 20s, that have more 20s than other energies. So now the question is there a target material that will yield characteristic monochromatic energy at 20 keV? Well, to get the 20 keV, you'd have to have a target material whose binding energy is 20 keV. Well, off to the periodic table, what material has a binding energy of 20 keV? And what you'll find is molybdenum. Molybdenum actually has characteristic radiation energies of 17.5 and 19.5. Remember that every material has a characteristic, what we call signature. Remember the signature of tungsten? It was 69, 58, and 10. Well, the signature of molybdenum is 19.5 and 17.5. It also has some much lower energies, but they just don't get through the tube. They don't get out. They get filtered out. So the important radiations for us are 17.5 and 19.5. Not quite 20, but it's as close to 20 as we're going to get. From now on, I'll always refer to molybdenum as having 20. In the back of your minds, it's very close to 20. Okay, so we've got a material. A molybdenum is a metal, so you can fashion a target out of it. And but now we find an additional feature. Okay, molybdenum is a low atomic number. But if it's a low atomic number, think of it. That means it doesn't have as many protons in the nucleus as tungsten does. Right? Atomic number is the number of protons in your nucleus. Well, so what if you don't have so many protons? Well, that means that as the electrons approach the nucleus, there won't be as much of an attractive force exerted upon those electrons. And that means that there won't be as many Bremsstrahlung events, and the events that do occur tend to be lower energies. The bottom line is Bremsstrahlung is not the dominant event, interaction, that when we use something like molybdenum, these low atomic number targets, monochromatic radiation now dominates. Hey, that's good. We wanted the monochromatic 20 keV line. So now we not only get the 20, but we get the 20 as being the dominant energy. Here it is. Here's a little table. Remember the tungsten we said was 80 to 90 Bremsstrahlung and only 10 to 20 characteristic? The tables are turned. Now the molybdenum, and later on I'm going to talk about rhodium, notice that now the dominant energy is your characteristic radiation interaction, which is just what we want, the 20 keV photon. Okay, and so now we answer the question, why do we use molybdenum and rhodium targets for molybdenum? For mammography? Because they yield the desired monochromatic energies for our for the applications in mammography. Simple as that. And this would be a a representation of the spectrum. You still have bremsstrahlung, but now you have that dominant characteristic peak at 20 keV. Okay? Well, we're not going to be satisfied with this, and notice that you have high energy components still there. They yield a reduction in subject contrast, and notice that you still have the low energy components. They yield those. What are we going to do about that? We'll look at that at our next session. Any questions before I let you loose over here? Okay, you all have a good day, and we'll catch you the next time. Have a good day.
Thank you.
Bye-bye. Thank you.
I was like, no.
Few thoughts for that.
One.